Okay, any more takers for the poll? Going once, going twice. We'll end the poll at this point. So should be able to see the poll results. So I think perhaps most interesting, a third of the class was born outside the United States, 2/3 within the United States. So interesting mix there. Only 3 native Hoosiers. And then like rest of Eastern Midwest 2. That doesn't include myself. I didn't vote, but I'm from Illinois. That's where I was born. And let's see, some Northeast, some South, a few Pacific people, 1 person from the DC or American territory. So I'm sure that's an interesting story. If it's a territory, but even still, if it's DC. And then for our foreign-born people, 2 from South America, 2 from Middle East, North Africa, 3 from East Asia, and 2 from South and Southeast Asia. So we don't have anyone from Canada, Mexico, Greenland, Central America, Europe, Sub-Saharan Africa, or Australia or Oceania who voted. So, okay. Let's close out of the polls and prepare to do class. So I'll share my screen. Screen 1. Should be able to see what I'm. Should be able to see Zoom right now, and everyone there. Looks like we're up to 40 people on the call. That's good. So let's start with a recap. So yesterday we did some examples, but we also talked about the early effect, also known as channel length modulation effect, whereby as we increase VDS in the saturation mode, we do get a slight change in the amount of drain current, whereas before we treated it as constant regardless of the drain to source voltage. All we did was add a term to our drain source equation that looks like 1 plus lambda VDS, where lambda is the channel length modulation parameter, units of 1/volts. And last time someone asked, how is this useful? How can we exploit this? You don't really exploit this. This is more of this is something that robs you of desired performance. So it's just one of those unfortunate reality things. And then we're going to adjust our circuit models by adding the incremental resistance R sub O, an output resistance, which is approximately 1/lambda ID. So based off our DC drain current and this channel length modulation parameter. We discussed a couple circuits that approximate a good current source. Then we talked about current steering, the process of replicating a desired current throughout an integrated circuit for purposes of biasing or loading. And we said that we need a current source and a current mirror, and it turns out that they basically are the same thing for us. So here's our basic MOSFET current source, also known as the current mirror. And one of these transistors is diode connected, the other is regularly connected. It sinks a current, Q1 sinks a current down through its drain. Q2 sinks the output current down through its drain. And we get this current transfer ratio, which is just the ratio of the aspect ratios of the 2 transistors. So if they are exactly the same aspect ratio, say, 5:5, then you get that IO is equal to IREF and you have perfectly duplicated current. Otherwise, you can scale the current by making WL2 10 and the other one 5. So you get a 2-to-1 increase in current. And it does depend on the early effect does modify our current transfer ratio equation to be more complicated. Again, this would be the kind of thing you would expect to find on an equation sheet or in the pages of the test if it was needed. But the important thing is we must keep the second transistor in saturation mode. So the output voltage, measured at its drain must be greater than the overdrive voltage for that transistor. We talked about this current steering circuit and how you could just sort of chain together multiple current transfer ratio equations to get, currents in different places that we can use for biasing or loading other circuits. And today we're going to talk about what those kinds of circuits are usually, and those are single transistor amplifiers. So we talked about, let me first check for questions. Bad case of the Thursdays. Where's everyone in terms of not where they were born, but people showing up to class? I get it now. I'm slow on the uptake. It's a Thursday. So, in digital applications, which, the vast majority of transistors in the world are used for, transistors are switches. So we're switching between, triode mode and cutoff mode, deep in triode mode and the cutoff mode. But we use amplifiers in the saturation mode for analog circuits because amplification is the single most common signal processing task. Later on, we'll talk about the second most common signal processing class in this course, which is filtering. We even touched on combining with things like the summing amplifier, which is a way to just add two signals together. So there are three basic single MOSFET amplifier configurations, and then we're going to analyze them in terms of three different metrics: gain, input resistance, and output resistance. So if you're ever asking, why do we need to study three of them? What's really the difference? It's these things: gain, input resistance, output resistance. The core of linearized operation, the recipe for success for us that makes it so that we go from very complicated nonlinear devices to linear amplifiers without distortion, is good DC biasing and small signal operation. So, yep, new slide. I'll let someone speak up if I miss a question. So the basis of transistor amplifiers is this control equation for the active region. So we're going to define active region so that it works regardless of the type of transistor we use. In my previous class, we dealt with BJTs and MOSFETs. Here we're just dealing with MOSFETs, so the active region is just another name for saturation mode. So by our square law relationships, the equation at the top of the page holds. The drain current is 1/2 Kn quantity VGS minus VTN quantity squared. You can see we didn't include the early effect. We're going to neglect it unless it's really easy to handle. So we're operating saturation mode. The channel is pinched off. And we're going to use NMOS transistors the most in this lecture set. Everything can simply be changed as we did in the previous slides for PMOS transistors. So, we had a slide about how you handle PMOS transistors and how you swap the polarity of voltages, and you sometimes use absolute value signs, what have you. So we need to make an almost linear amplifier from this very nonlinear control relationship, where here we've got, a current that is proportional to a voltage squared. That's not very linear. That's about as textbook nonlinear as you can get. So the active region equations are nonlinear transconductance relationships. By transconductance, we mean that there is a control voltage in, and then we have this driving current out. So here you can see VGS would be considered our input, and then the output is a current at the drain. The easiest way to get a voltage amplifier from this is to simply convert the output current to an output voltage using Ohm's law. So if we include a load resistance in the drain, RD, that means, we're going to get a voltage out that's proportional to the current. We're going to see that it's much better to have the input and output voltage share a common ground reference rather than take it differentially across a floating resistor that doesn't have one of its terminals connected to ground. Therefore, we're just going to take the output voltage between the drain and ground instead. So equations from KVL for a grounded source amplifier is going to be VDS equals VDD minus RDID. So what does that sort of circuit look like? It looks like this. So here we can see we're applying a voltage between the gate and the source of this NMOS transistor. And we're taking the output at the drain terminal with respect to ground. So since the source is grounded, that's just VDS in this case. And then we have this resistance up here, where if we do KVL, we get that VDS is just VDD minus RDID. And we know what ID has to be based off of this equation right here. So for saturation mode, we can also plug in the equations for the other modes of operation, where ID is equal to 0 and cutoff. So we just get VO is equal to VDD. We have the more complicated saturation mode equation, which produces a curve that looks like this between points A and B. And then we have the triode, or yeah, excuse me, that will be saturation mode equation. And then we have the triode mode past that, which happens when VDS sinks below the overdrive voltage, and then we get this B to C sort of characteristic for triode mode. So yeah, we can just plot the various modes of operation for this transistor, and we can see what VDS looks like as a function of VGS. So this is an output to input voltage. We call this a voltage transfer characteristic in microelectronics world. Any questions up to this point? Okay, hearing none, I'll press on. So after we've done this little bit of preparatory work, let's talk a little bit about small signal FET models. So the first thing we need to know is how DC biasing works. So we're first going to apply a DC voltage. Oh, yes.
Oh, sorry. Sorry, my mic wasn't working earlier, but I wanted you to explain that graph a little bit more. I really didn't get it.
This graph of VDS versus VGS.
Yeah.
So I guess the first thing is VDS follows this equation. Do we agree about that?
Yes.
So we also have equations for ID based off of the various modes of operation.
Okay.
So this is saturation mode. So I can plug this nonlinear equation into this equation, KVL equation for VDS, and I can get, for example, this curve right here.
Okay.
Which basically says when VGS is greater than the threshold voltage, because there's this minus sign here, it looks like this the semi-parabola, but now it's facing downwards.
Mm-hmm.
And then in cutoff mode, whenever VGS is less than the threshold voltage, no current can flow through the channel of the MOSFET. That means no current can flow anywhere into any of the terminals. So we just get that VDD minus 0 equals the output voltage VDS.
Oh, I got it. That makes more sense.
So that's how you get this segment of the curve, this saturation mode. And then you'll notice at some point the voltage across RDID, the voltage across this resistor gets too big, and then that causes this point of VO to be lower than the overdrive voltage noted right here. At this point, this becomes lower than the overdrive voltage, and then we switch into triode mode, and then we have to bring out a triode mode equation, which is Kn quantity VGS minus VTN times close quantity times VDS minus VDS squared. Bring that equation out, and we get this sort of like weird cubic relationship right here. It's a little hard to plot.
I got you. What happens at the very end, on the far right of that graph, where it just like kind of drops all the way at C? Is that cut off
so
again?
That's the point. So at that point, the voltage has become equal to VDD. And we just say, like, technically you could apply a voltage bigger than your source voltage if you had a split supply, but you wouldn't do that in practice.
Okay. Thank you.
You wouldn't want to have two different supplies. So I just said, C is the last point we care about, because we've gotten the full extent of our two power supply voltages, ground and VDD.
Gotcha. All right. Thank you.
You're welcome. Okay, so FET DC bias point. So remember, the core of linearized operation, good DC biasing and small signal operation. So let's first talk about the DC biasing. So in this very simple example, normally you would use a much better biasing network like that 4-resistor network we did in the last lecture. Excuse me. We're going to apply this capital V sub capital GS, which is our DC voltage. And then we're also going to superimpose on it little v sub little gs, which is a purely AC quantity. And then, together they are v little v sub capital GS, the total gate to source voltage. It's basically saying we can break up any voltage into its DC component plus everything else, the AC component. So we know that, the bias current is ID is going to be 1/2 Kn V capital VOV squared, where that is capital VGS minus VTN, right? That's just the definition of the overdrive voltage. It just saves a little bit of space in a set of parentheses. And then we have that same equation from before, VDS is equal to VDD minus RDID, except now we're looking at the DC quantities. And then the condition to stay in the active region is we must have VDS greater than the overdrive voltage with some added legroom. So you don't want to be right at or very close to the overdrive voltage. Otherwise, when the output swings low, it might take us into triode mode. And we wouldn't like that. It would cause weird flattening of our amplifier output. And the nice thing is our bias calculations with the DC parts are going to stay separate from all of our small signal calculations. So that means once you do the DC biasing calculations, done. You just kind of save them, write them in a little box in the corner, and then you use those values for all your AC calculations. Nothing you do with your AC calculations should be able to change your DC bias calculations. And those DC bias calculations are just like the problem we did yesterday's lecture. So here is a little bit of a derivation to see what's going on. So the total gate to source voltage is the DC bias component plus the AC component. So all capital letters plus all lowercase letters. This equation right here is pretty strong. It applies to, mixed signal operation where we got, not mixed signal, but large and small signals. So we can just plug everything in and we substitute for VGS into this equation, the DC component and the AC component. Now we can move some terms around when we expand the square. So we'll have VGS minus VTN quantity squared plus twice the cross term. So that twice cancels out the 1/2. So we get Kn VGS minus VTN quantity times little VGS, and then plus the center term squared, 1/2 Kn VGS quantity squared. And if we look very carefully at this equation, we'll note that the total drain current is a DC drain current. This is all DC quantities, plus an AC term that's proportional to VGS, where this term right here looks just like a conductance. Conductance being 1/resistance. And then we have this last term, which is proportional to the signal squared. If you square a sinusoidal signal, you get something that oscillates at twice the frequency. So you have changed the shape of the waveform. So this is just distortion. What I'm trying to convince you is that if we have sufficiently small signals, we have just the small signal current, little I sub little d, and then the distortion term that's quadratic goes away. And then how can we do that? Well, if we look at this equation and we say, okay, I want the 1/2 Kn VGS square term to be much, much smaller than the second term, Kn times quantity capital VGS minus Vtn times little vgs, we get our small signal condition that will say that, the last term goes away and we can avoid nonlinearity, which is that VGS must be much less than twice the overdrive voltage. So say, for example, we're using an overdrive voltage of, half a volt. Now that's a little unrealistic. Let's say we're using an overdrive voltage of 1 volt. If we're using an overdrive voltage of 1 volt, that basically says, hey, we should be less than 0.2 volts for VGS. So the amplitude of our small signal voltage should be smaller than 0.2 volts. What questions do we have to this point? No questions? Okay. So we've derived the small signal condition. We've talked about DC biasing. We should be good to go to get a linear amplifier. So looking at this little I sub little d term, our small signal current, we can define a new parameter that will we use in our future circuit models, and that's called MOSFET transconductance, little g sub little m. It's an important parameter. It's going to show up in our small single MOSFET amplifier gate expressions a lot. Basically, you can think of it as the partial derivative of little I sub little d, this middle term right here, with respect to VGS. At VGS is equal to some capital VGS. So then that's going to be equal to the overdrive voltage. So, Kn MOSFET transconductance parameter times the overdrive voltage, yeah. So the interpretation of GM, if you want to know what is MOSFET transconductance like really mean? Like, it's a number that shows up a lot, but like, how do I figure out what it means? So if we think about the 4 generic linear amplifier types, like you can have voltage in, voltage out, current in, current out, current in, voltage out, voltage in, current out. We're dealing with the last one, which is voltage in, current out. So how do you relate voltage in to current out? With a transconductance. So, the current out is equal to the transconductance times the voltage in. And specifically, it's lowercase because it's small signal. And it's called the short circuit transconductance because that's how you would characterize it, is you would short circuit the output to figure out what it is. You don't want to apply a load to it. That would change the circuit. If that's a little confusing to you, let me know. But the idea is that, this is a voltage in, current out type of amplifier, and this parameter, little g sub m, is what characterizes it. Formally, little g sub m is the slope of the ID VGS characteristic at the bias point. So if we go back to this graph and say we're biased at a point that's just above point B, then the slope at this point is what GCM is. Actually, no, that's not entirely correct. It should be the ID VGS characteristic, because that's negative. We have to go back quite a ways. ID VGS characteristic, it would be the slope on this graph right here. So as you can see, in a very small vicinity around, say, 3 volts, this looks like a straight line. As you make a farther and farther excursion away from 3 volts, that line and the curve no longer overlap very well. If we go back to slide 58, we can see There's other ways to calculate GM besides just Kn times VOV. Remember that an IC designer can choose what the aspect ratio W over L is. So, someone who's actually designing circuits would be able to control that parameter. So we've got, GM is equal to Kn prime W over L, VGS minus VTN, the expanded form of the equation at the top, where you see it depends on the geometry and the overdrive voltage. If you massage the equations around, you get GM is equal to the square root of 2 mu n oxide capacitance per unit area times aspect ratio times the square root of ID, where everything here is just parameters and the design geometry, and then it's proportional to the square root of current. And then lastly, GM is equal to 2 ID over VOV, where it depends on both bias quantities instead. Any questions? I'll move on. So FET voltage gain. So we said, that the total drain current is the DC drain current plus the small signal drain current plus distortion. What if we look at the output voltage? Because again, we want to create voltage amplifiers. We like dealing with voltages. Currents are kind of treated as second-class signals in signal processing land. So, we want voltage out as well. So if we look at our equation for the voltage out, VDS is going to be approximately equal to VDD minus RD times the combined DC drain current and the small signal drain current. Rearrange this a little bit, we see that we have DC bits and then the AC bit. So VDS is equal to the DC drain to source voltage minus GM VGS RD. So the total instantaneous drain voltage, VDS, has a DC drain voltage, capital V sub DS. The small signal drain voltage, which looks like this right here, under the small signal condition. So there's a distortion term that we're going to ignore because of the small signal condition. We get to ignore that. So the voltage gain is the ratio of the output, little v sub ds, small signal drain voltage, to the input small signal gate voltage. And if you look at this, you get that it's negative GM times RD. Notice that GM times RD, units of 1 over ohms times ohms. It's a unitless quantity. And it's also negative. So negative means that it inverts the voltage. So if you apply something that looks like a sine wave going in, what you get is a negative sine wave coming out. And then we're making some assumptions about the range of values for our voltages. The maximum value of VDS, the total drain to source voltage, is going to be less than the supply voltage, and the minimum drain to source voltage is going to be greater than the maximum gate to source voltage minus VTN. Basically, this one assures that we're not in cutoff. This one assures that we are not in triode mode. So, and again, A sub V is a gain. V reminds you that it's a voltage gain. Some books can use a different notation. So the other big things we need to cover today are the models for the transistor. So what is a small signal model look like? So here is one of the small signal models for the MOSFET. So when do we get to use small signal models? When we're dealing with AC quantities as inputs, that needs to be there. If we're dealing with anything related to DC, we have to use large signal models. And again, small signal models only apply when we have, small signals. So we meet our small signal condition. So VGS is much, much less than twice the overdrive voltage. And we have DC biasing to, create these values like V overdrive. You can't have, a small signal model calculated in isolation from its DC biasing. So if we look here, we have gate, source, and drain, the three major terminals of the MOSFET. There's no current into the gate because it's open circuited. That makes sense. But we do need to measure the voltage between gate and source so that we can have this voltage controlled current source, VCCS, with transconductance G sub M. And we also have this output resistance R sub O, which comes from the early effect. So if we have lambda, it sets RO equals absolute value of VA over ID, with ID as used in the DC bias calculations. If you want to think about all the parameters that go into calculating GM, you have electron mobility for an N-channel MOSFET, oxide capacitance per unit area, and aspect ratio. This view replaces one of the parameters, and then the threshold voltage. This view replaces one parameter with 4. I don't think this way. Think in terms of GM and channel length modulation parameter. So when using a small signal model, replace the transistor with the equivalent circuit. So you'll just substitute in this where you see the terminals of your transistor, and you must create the rest of the small signal equivalent circuit. So that means you replace independent DC voltage sources with short circuits and independent DC current sources with open circuits. I'll repeat that. If you have an independent DC voltage source, like a battery or the plus minus symbol or the supply symbols, like, the little arrow that says VDD or V plus or V minus, you replace that with a short circuit. Usually that's a short circuit to ground because the other side of the DC voltage source is connected to ground. An independent DC current source becomes an open circuit. That's how you turn it off. So if we go back to our example of this circuit right here, where we this basic grounded NMOS amplifier, when we include the early effect, we get that the voltage gain is negative GM RD in parallel with RO. So in a way, that equation I'm giving is a reference back to slide 55. And the key thing is if you have a PMOS transistor, you use the exact same circuit model. You do not swap polarities. You do not flip the circuit around. You connect gain, source, and drain to the exact same places. However, you need to use absolute value signs. Absolute value of VGS, absolute value of VTP, absolute value of the overdrive voltage, absolute value of VA, and you obviously use the P-channel MOSFET transconductance parameter. So you don't need to flip the circuit model around. You just work with flipped values instead. Any questions about this?
I'm a little bit confused because you say you use like GM as a parameter, right?
Yes.
But couldn't that be like variable because can't VGS change, or do I have that wrong?
So if we go back to slide 56, we basically said once you calculate capital V sub GS, it should be a fixed value. You wouldn't change your DC biasing while you're trying to amplify a signal. So basically nothing should change your DC bias point during the course of the operation of the amplifier.
I see. All right, thank you.
So that's why we're treating it like a constant. Otherwise, our math would get a little bit more messy. Any other questions? So there's one other model, which your textbook doesn't really cover, but is a little bit handier to use sometimes. So this is the low frequency equivalent T model. It's a counterpart of the hybrid pi model. So you can see we got gate and source, and then we've got this resistance 1/GM with a current of I flowing through it. And then this is a current controlled current source that ensures that the same amount of current flows through the bottom side of this resistance and the top side of it as well. You'll notice that even though it looks like there's a path for current to flow through G, this current controlled current source ensures that the current going down through this node or down into this node is the same that goes down out of the node. So that means there must be zero current flowing left to right into the node. I'll repeat that. The current flowing from the top equals the current going down through the bottom. So that means there must be zero current flowing rightwards into that node from the external gate. So again, this is completely linear under small signal condition that VGS is much less than twice the overdrive voltage. Two parameters, GM and then lambda, used to set RO using the DC bias gain calculation. And then the equivalent T model is an equivalent to the hybrid pi model, hence the name. It's just preferable to use whenever there's a resistance connected in series with the source. So some problems will get easier to solve if you put if there's a resistance in series with the source and the rest external circuit. The circuit model gets a little bit easier to use and solve problems. You can ignore everything about the equivalent T model if you don't like it. You can use the hybrid pi model for everything. You just have to be a little bit more clever with the circuit tricks you use to solve circuits. Do we have any questions?
I'm just assuming that voltage gain is the same for T model and pi model.
Yes, you will calculate.
Okay.
If you were to use it, you would get the same result.
Okay.
Any other questions? So one more topic for today is we have to talk about active loads. And I really only have a single slide on this. So your textbook goes a little bit more in depth and then doesn't really build on this information. So I decided to trim some stuff out here. So the idea is that because transistors are smaller than resistors in an integrated circuit, like, a resistor might be 1,000 times bigger than a transistor, not even kidding. At least in terms of like the length. It's desirable to replace all the load resistors with more transistors. So, here we used a load resistance RD in order to convert from a transconductance amplifier to a voltage amplifier. What if we could use another transistor instead? So the key point is that because our low frequency models have this resistance RO between drain and source, so this output resistance from the channel length modulation effects, it provides a very large resistance for circuit purposes. So we can basically say, if we were to ignore RD, set RD equal to infinity, and just have a second resistor out there, we would basically get RO in parallel. Well, I'll rephrase myself because that's confusing to you. If we were to replace RD with the RO from another transistor, we would get minus GM RO in parallel with RO, or, negative 1/2 GM RO, which, RO is usually big. If it's a discrete transistor, it might be in the hundreds of kilo ohms. If it's inside an integrated circuit, it might be in the 10 kilo ohm or thereabouts area. So there's an advantage to using the large output resistance, because as you can see, even though, we get a larger magnitude of gain that way, it's negative. So, instead of having a gain of negative 20 by using a discrete resistor, we might get a gain of negative 50 using another transistor as an active load. And that would be really good for us. So for a good Q point, there's a large AC signal swing allowed while staying in the active region. So basically, if you go back to the ID versus VDS characteristics, you see, because the early effect has, this sort of very, shallow slope, you get a large range of variation in VDS for a small variation in ID. So that basically says you get a large AC signal swing, because you can swing the input very large over a large interval, but have a very small interval of change for the drain current, and hence the drain to source voltage of your output. And then here are two ways you can create an active load. So the first should be familiar as the diode connected transistor. So this is an enhancement type NMOS transistor. If we use a depletion type NMOS transistor, we can connect the gate to the source instead. And since there's a channel implanted, even though the gate to source voltage is 0, there's still a way for current to flow down through this device. This looks very similar to this detour JFET current sink, just using an enhancement or a depletion type NMOS instead. Do we have any questions? Hearing no questions, we talked about how you calculate the output resistance. We talked about how you calculate GM. Now it's time to put everything to the test and talk about amplifiers. So I'm going to move on to some of the Chapter 5 material, which is common source amplifiers. So first of all, why do we need amplifiers? It seems like a rather arcane bit of knowledge. Why should we do it? Well, as I said before, amplification is the single most common signal processing task. Any sort of transducer, which is, anything that creates energy in a different domain from it receives as its input. Another name for them is like sensors. So a sensor might be something that, translates vibration into a voltage, or maybe, but like a microphone, or it might translate temperature into a voltage, like a thermoelectric element. They only produce weak voltages where information can easily be lost among the noise. So if you have a signal amplifier, you can increase the magnitude of the input at the output. So we want an amplifier to be linear in order to preserve the information without changing it. So it needs to be, the output needs to be the exact same shape, just with a larger magnitude compared to the input. Any sort of nonlinearity in our amplifier will cause distortion. So the magnitude and phase of different frequency components will be changed differently from each other, or could introduce new frequency content altogether. So that changes the amount of information compared to the base transducer output. So you wouldn't want that. So there's, if you're an applications person, you would divide electrical amplifiers into two categories. Voltage amplifiers are on the source side, and they're used to enlarge the signal magnitude. And then you talk about power amplifiers or current amplifiers on the load side in order to drive loads based on your requirements. So the most generic amplifier signal looks like this, where, okay, it's got this connection to ground, and takes an input and an output, and it's got in the mid labeled on it AV, some voltage gain. So it basically says VO is going to be AV times VI. You'll notice this is very similar to the op-amp symbol. It's just made even more generic because it only has one input instead of two outputs, or one input instead of two inputs, rather. So if it's a voltage amplifier, it uses AV, A sub V. If it's a current amplifier, it uses A sub I. Or you can calculate it by saying how IO changes compared to II, the input current. And then you can talk about the power gain of an amplifier, A sub P, which is the power delivered to the load over the power received at the input, which is just VO times IO over VI times II, which is the product of the voltage and current gains, as you would expect. Most of the time we talk about gain in decibels, though. So you can talk about voltage gain as being 20 times the log base 10 of the absolute value of AV. That produces an answer in decibels. Very similar for current gain. The thing to watch out is power gain doesn't use 20 times log base 10. It uses 10 times log base 10 because it's a product. So it's 10 times log base 10 of A sub P to get the decibel answer. Anytime the gain is negative means the output is 180 degrees phase shifted. And then if the gain is less than unity, or you have negative decibels, because plugging any number smaller than 1 into a logarithm produces something that is negative. That means you're attenuating instead of causing amplification. You're scaling down instead of scaling up. So anytime you see a gain less than 1, that means the output is smaller than the input. It's attenuated. So sometimes we ask questions about the power balance for an amplifier. By conservation of energy, you can either create nor destroy power. So gain is only possible thanks to the DC power supplies. The DC power supplies are typically omitted from the amplifier symbol. But basically, here's the power balance. So power in must equal the power out. So the DC power supplied by the DC power supplies, PDC, plus the power into the device, PI, must equal the power delivered to the load plus the losses. So we usually use efficiency as a percentage instead of a decimal. Eta is our variable for efficiency. That's defined as power delivered to the load over the DC power supply, the power supply by the supplies, plus the input current, all times 100%. But most of the time, P sub I is very small. So PL over PDC times 100% is a good approximation of efficiency. I want to emphasize this point a little bit more strongly. So how do we create gain? You might wonder, like, how does a MOSFET, this, 3-terminal device, this, piece of silicon and, a little bit of phosphorus and boron mixed in, possibly create, power gain? How does it make signals bigger? Because that doesn't seem to obey conservation of energy. It does, because what it's doing is it's translating power from the input side from its DC supplies. So it's taking power from the DC biasing and turning it into the load power delivered, as well as losses. So that's what's going on here. Any questions? Oh boy, a lot of questions. Active loads are the end of chapter 4. Yep. Formulas to give, which formulas on the equation sheet said? Examples of the pi model in a specific circuit to help understanding. Basically, chapters 5 and chapter 6 use the pi model in the single transistor amplifier configurations to help you see how they're used. Yes, the other name is mid-frequency. I mean, the low frequency and mid-frequency models of the transistor itself are the same. So it's low relative to the high frequency models, which are different. You're welcome, Daniel. Yeah, the transistor model isn't what changes when you go from mid-frequency to low frequency. It's all your external connections that dominate the effect. I would consider the decibel equations ones that you need to memorize. If it does end up on an equation sheet, it's because I'm feeling very generous. But you should memorize these equations. It'll help you out in the long run. You need to know when you use absolute value signs. It's always a log base 10, and when you use 20 instead of 10. Like, engineers in the field still get confused about this to this day. So I would definitely keep these in mind. Are the models like Thevenin and Norton for transistors? Not really, because they both use current control current sources, and it's not like you're changing a voltage source into a current source by source transformation. It's just what it did is it basically took this pi model where it's shaped like the letter pi, and this T model where it's like a sideways T, and it just put the right components in the right places in order to get them. I wouldn't call them Thevenin and Norton equivalents of each other, though they are duals of each other. So in that sense, I guess they are like Thevenin and Norton. The examples will be coming up soon. You'll see examples starting on slide 73. Is there a specific circuit? David, no. It's a replacement for the transistor itself. So it's a model of the small signal behavior of the transistor in isolation.
Sorry, I have one more thing.
I'm going to move on a bit.
Can I ask something really quick?
Yes, you can also ask it
Okay.
slowly, but I'll be
Sorry.
a little annoyed.
Okay. For the quantities of gain, is power halved because of the 1 over square root 2 being squared
No.
from effective? Okay.
It's halved because it's a product of two gains itself.
Okay.
So like the idea is that this is always confusing to put into words. The idea is that voltage gain represents what it would be like if it were a power, because normally decibels would be 10 times something. Deci means, a tenth of something. So
Right.
It's 10 times larger. It's basically you would take the voltage and you would square them, because that would be a representation of what happens to the power.
Okay. Got it.
And then because you can think of it as P equals V times I, or V squared over R. And then this is R times I squared. And then this is just, power itself. You don't need to square it.
Yeah, that makes sense.
Idea.
Thank you.
Oh, I'm glad it makes sense, because it doesn't make sense to me sometimes.
Well, that makes more sense, I guess.
Okay. All right. Slide 66. We're on a roll today, and I like that. The voltage amplifier circuit model. So here's a basic amplifier circuit model. So we have the source. Here we're using its Thevenin equivalent of Vs and then an Rs. And then in the middle, we have the amplifier block, where it's got an input resistance like this. And then it's got its voltage controlled voltage source and an output resistance associated with it. And then the load block is just a resistor. So basically, you can analyze this with voltage divider equations galore. So what is the output voltage in terms of the input voltage? Well, VO is just whatever the voltage of this source is, AVO times VI, times the lower resistance RL over the sum of the two resistances RO plus RL. Okay, so that's one equation. So if we want to talk about the amplifier voltage gain, it's just VO is to VI. So that's just AVO times RL over RL plus RO. Where our AVO is just the open circuit voltage gain, or the voltage gain you would get if RL was equal to infinity. So that's how you would characterize it, is by doing an open circuit test of this amplifier block. Next, we can go a little bit further back. How do we get where VI is? Well, VI is equal to the source voltage times the lower resistance RI over the sum of the two resistance RS plus RI. So if we wanted VO is to VS, we just figure out, we can write that as VO is to VI as VI is to VS, or AVO times RI over RI plus RS plus RL over RL plus RO. If you want to maximize the gain, overall voltage gain, we can design the amplifier, so we should figure out what we need to do to RO and RI. We want RO to be as small as possible compared to the load, and we want RI to be as large as possible compared to the source in order to maximize the gain, because we want these multipliers, voltage divider multipliers, to be equal to 1, or as close to 1 as we can get. So that's how you quickly analyze the circuit, just using the voltage divider equation twice, and then using definitions of gain. So that's the voltage amplifiers. So what about all the other types of amplifiers? Here's another table from Sedgwick and Smith. So here's the 4 amplifier types, where I mentioned voltage amplifier with open circuit voltage gain, AVO, current amplifier with short circuit current gain, AIS, transconductance amplifier, remember that's voltage in, current out. That uses capital G sub M, IO, which is IO over VI when short circuited. And then transresistance amplifier, voltage or current and voltage out, which uses open circuit transresistance as defined here. So, oh my gosh, I just complicated things, because we talk about voltage amplifiers and transconductance amplifiers. Now there's current amplifiers and transresistance amplifiers. Do not fret. All of these 4 amplifier types are related to one another. You can transform one into the other by means of these equations right here. Open circuit voltage gain is unitless in terms of the other gain parameters. So I just showed you how you get the voltage amplifier from the other type of configurations. And this is definitely using Thevenin and Norton ideas here. In practice, if you were to measure RO and if you're to measure RI and RO, you can't just apply a test voltage and measure the resulting current. You need a little bit more sophisticated equipment if you're going to do this in practice. But, the idea is that we can always translate one of these amplifier models into any of the other ones. So that's the sort of basics of amplifiers, like the generic amplifier. We're going to talk about how you actually build amplifiers. And for that, we're going to hold off until tomorrow, where we'll start on good old slide 69. We'll talk about the procedure we're going to have for analyzing amplifier circuits. Do we have any questions?
Professor,
We'll receive what formulas we're going to be given before the exam. Jarrett, yes, you will receive the equation sheet 1 week in advance, as Aubrey reminded us. And Siraj, what was your question?
Will we get additional practice problems other than the homework problems? Because I am quite concerned about lack of practice. Because the content itself makes sense, but I feel like I'm not confident enough to apply them.
The answer really is, unfortunately, the short answer is no, because we have limited time in order to develop questions in time. If we were to give out more questions, they wouldn't be graded, just because with the number of students in this class, we just don't have the time to keep giving out extra assignments and grading them.
Not necessarily as assignments, but like rather than assignments, maybe like exams from past semesters of sorts, just so that we can practice on our own for those of us.
Right. I will see what I can dig up today, and I'll post them if I can.
Got it. Thank you.
Jeff, you had a question about homework. It's after time already. Thank you everyone for your attention. If you don't have a question, feel free to leave or visit me in office hours if I don't get to your question in time. Sayla, when analyzing ID SAT, any DC term multiplied by AC term is an AC term? Yes, because it will depend on, the actual variations in AC. For problem 3, is there a set of correct resistance values? I will say, if put the gate resistances into the tens of mega ohms and put the drain and source resistors in the thousands of kilo ohms, or not thousands of kilo ohms, into the single kilo ohm range. Those would be the most realistic values to give. Hope that answers your question, Jeff. Any other questions? If not, I'm going to go ahead and end the call. Thank you very much for your attention. See you tomorrow.